Okay, so thank you for the kind introduction, and also welcome from my side. So after having dived very deep into these numerics and mathematics in the previous talks, I will go to a different topic and focus more on experimental things. So it might be a bit more relaxing for some of you. So this project was already mentioned in a few talks during this conference, and probably not all of you are experts for filtration. So if you have not yet heard of this word Electret filters, so it means you have a non-woven fibrous filter material, and there are electrostatic charges on the fibers. So that's the definition of Electret filter. So why do you do this? Typically, particles in the air are charged, and if you have charges on the fibers, there is some electrostatic attraction between them, and you can increase the efficiency, but you do not change the structure of your medium. And by this, there is no effect on the pressure drop. So you can increase the efficiency without affecting the pressure drop, and this is a nice reason why you use Electret filters. So you may think this is something very fancy, exotic, but actually they are very often used in applications. For example, most filters for ventilation systems make use of Electret filters, and especially in applications where you need this low pressure drop, like indoor air cleaners, filters for vehicle cabin air filters, they make use of it. And a very common example are respirators or face masks. So all of you have probably been in very close contact to an Electret filter already. So this sounds all very nice and perfect, but there's also a major drawback of these Electret filters. And this is that these charges can get lost over time. So what you see here in this, I will try to use the pointer. What you see here, this is for two different media, and you see the filtration efficiency as a function of particle size, and they perform quite well here, somewhere in the 60 to 80% efficiency range in the new state. But if you discharge them, so we will come to this later, how to do this, you see the efficiency goes down very much. So and if you want to learn more about these effects and optimize your filtering media, it's crucial to learn more about these discharging processes. If you want to learn more about the filters, there are basically three approaches which you can do. So first is just testing the filter media, and that's probably the most direct approach. You test the actual filter medium. You have a lot of highly scientific equipment to do this. But the problem is if you want to change parameters, you have to produce a lot of samples, and it's quite some effort to do this. And also if you want to use these aging studies to see what happens on the long term, this takes very long and is especially costly then. The second approach, so filtration theory, is known for decades. So there are lots of empirical modules. So we heard this in the question before. The problem is there is not one formula, but you find a lot of them, and you have really to be an expert to choose which is the right one, which is valid for which range of parameters. So it's not very easy to implement, and it's also just for very simple filter media. As soon as you have certain gradients, complex orientations, these easy models do not really apply. So this brings us to the third approach, which is somehow directly implementing the physics and modeling the real filter medium, which is rather easy to use, something like GeoDict for consumers. You can do flexible parameter studies, and if you want to change parameters, you do not need to produce new filters, but you can just do this virtually in a digital twin. So you can do some, let's say, cost and time efficient investigation of these Electret filters. But of course, if you introduce this, you want to validate this with experiments so that you have a high trust in the simulations. And that's the aim of this project ELEXIM. So it's a publicly funded project. And we want to model the efficiency and long-term stability of these Electret filters. And we, of course, do not start from scratch, but we set up on GeoDict, which can basically deal with different filter media types. You can have different parameters for your filter media. You can model the filtration process. You can also model loading processes. But these electrostatics were only very basically implemented up to now. And we focused on improving the capabilities for these electrostatic effects. So this brings me to the agenda of my talk. So I will first talk a bit about which things we had to implement in the beginning as for the basic functionalities. Then we did verifications with an independent CFD program to see if everything is correctly implemented. And then we compare our data with experiments to do this validation. And then the last part, I will talk about our ideas how to implement these discharging effects in the software. So I probably do not need to say a lot about GeoDict because you have heard about this in the previous talk. So what you basically can do, you can generate a model or import it as a micro-dissecant. You calculate the flow field. You can track particles. They are deposited. And if you want, you can, after deposition, recalculate the field and iterate this if you want to simulate these loading processes. So that's already all implemented. So the main thing we have to focus is this tracking stage where certain aspects need to be added for these electrostatic considerations. So the first thing is the particles carry a certain charge. So in the software, there is an option to assign different charges to the particles. And what is very common is this so-called bipolar equilibrium state, which is called here in the software Boltzmann random. So you have ions in the air, positive and negative ions, and they interact with the particles. And if you give long enough time, there will be an equilibrium charge distribution. And this depends on particle size. You see, for example, if you look here at 10 nanometer particles, about 90% are uncharged. Some carry one positive or one negative charge. And if you increase the particle size, this distribution smears out and becomes flatter. And you also see it's slightly shifted to the negative side. This is because the negative ions in the air are more mobile than the positive ones. So there's a preference to have negatively charged particles. So this bit complex but well-known size distribution, charge distribution of the particles now implemented in the software, and there are also different options which you can use, for example, for testing purposes. The next thing is the charge of the fibers, and that's a rather complicated topic because there is actually no easy method to measure the charge on the fibers. So which level of surface charge density do I have? How is the charge distributed? But if you look at the literature, there are at least different approaches how it could look like. So depending on your filter medium, it could be charged in different layers. So here we have gray are neutral parts, blue is positive, red is negative, or vice versa. There are publications which propose more something like these island structures where you have different charges on very small scales. And there are also special types where you can have so-called split fibers which carry both charges on the same fiber. So the software was adapted in that way that you can assign these different charge distributions. And to be honest, probably we will not reach the state that you have a filter medium and you can just predict how it will perform without having any information about the charge distribution. But if you want to compare different parameters, that's actually not a big problem. So you use it as a fitting parameter based on some experimental data, and then you can compare different variations of your parameters. So we have charges on particles, fibers. The third thing we need is the implementation of the actual physics. So this is how you track the particles. You have this Lagrangian model, so it's basically Newton's law. You have some drag force by resistance of the air. You have some stochastical process to model diffusion of the particles. If you have large particles, also gravity can come into play. And we added these electrostatics, and this consists of two parts. So the first one is easy and probably easy to understand for everybody. You have a charged fiber and a charged particle, and there is Coulomb attraction, and the particle will move towards the fiber. But there is a second effect, which is less known, which is called dielectrophoresis. So if you have a charged fiber and a neutral particle, the particle will be polarized. So you have more negative charges on the one side and more positive charges on the other side. And if you have then a gradient in your electrical field, the particle will also move to the fiber. And you see dipole is something like charge times length. So you have more space in a large particle. So it's more relevant for large particles than for small particles. And you see this here by this particle diameter cube which enters. So that's for the large particles, where this is more relevant for the small particles because they are more mobile. And the third thing you need to do is to calculate the electrical field, and that's quite easy. You have to solve this Poisson equation with a certain boundary conditions for the surface charge density, and you just form the gradient of the potential and you get the electric field. Okay, so we implemented all these steps in GeoDict, and we compared it to ANSYS Fluent, so to have a completely independent model and to see if all these effects are correctly implemented. And then the first thing we saw, it didn't fit very well. And we were reasoning what's the reason for that. And it's a very fundamental thing. If you think of something like Fluent, it models a very smooth surface. And in GeoDict, you have these voxels. So it's, of course, quite exaggerated here in this picture. And if you apply the same surface charge, it refers to different surfaces. So the red surface here in Fluent is larger than the yellow one in GeoDict. And we considered this effect and corrected for it. It sounds quite easy, but it depends on the voxel size, it depends on the curvature, it depends on overlap of fibers, but that's not all implemented. And then you get exactly the same results if you enter the same surface charge density. And we studied these for 2 cases. So first, a very academic case of a single fiber. And here you see without any charges, you have this typical U-shaped filtration efficiency. So this is caused for diffusion by the small particles. It's caused by impaction, so inertia for the large particles, and you have a minimum in between. If you add the electrophoresis, you see there is a strong increase for the small particles. And if you also add dielectrophoresis, you get a further increase for the large particles. We also did this for a slightly larger structure here with about 10 fibers. And again, you have these U-shaped case for just mechanical effects. Strong increase by electrophoresis for the small particles, and also for the large particles. You see there are still some slight discrepancies, but in principle they match very well. So the physical effects seem to be implemented correctly all. Okay, then we come to the experimental part. So this is actually my part. So we are doing filtration experiments at our institute. So we took samples of 100 square centimeters of different filter media. And we have, for example, this filter media test rig, which you see here, where you dose particles from the top. The filter medium is somewhere here, and you measure the number of particles without and with filter, and by comparing these numbers, you get the filtration efficiency. We can dose different types of particles. For example, here we used salt particles and DHS, that's a kind of oil droplets. You see here the size distribution. So the salt particles are somewhere in the 80 nanometer range, the maximum, the oil droplets are slightly larger. We measure with a so-called mobility particle size spectrometer, where you can cover this range from a few dozens nanometers up to 1 micrometer, which is actually most relevant to find the minimum of this curve. And we use this charged media, and as reference, we always want to use a completely discharged medium where we only see these mechanical effects. And there is a standardized way to do this. So you put your filter medium in such a chamber, and there you have isopropanol vapor, and you expose it for 24 hours to this isopropanol vapor, and all the charges will get lost, and then you have a purely mechanical filter medium. So that's always our reference. So which media did we take? We asked different companies if they can provide something which could be well suited for our study, and we had here 5 different media. You see they are charged with different methods. So corona charge means you have corona needles, you produce ions and they attach to the filter medium. That's a very common way. We have triboelectrically charged. There you have 2 different polymers in your material, and by friction there is charge separation. You notice if you rub on some material, you get these charge separation. That's basically the same process in the filter. And we had hydrocharged filters. There you have your filter medium and you shoot, or your fiber, and you shoot a water jet on it. And by this, charges are removed from the fiber, and you get also charging. So these are the 3 most common ways to charge filter media. And we did a kind of screening. So what you always see here in blue is the filter efficiency of the new medium, and in red after discharging it. And you see for all these media, you have a very pronounced Electret filter effect. So we want to decide which is the best material to start with. And you see here for filter medium B, you have a high scatter if you test 3 different samples of the same material. That's certainly not what you want to have. So we excluded this at the beginning. Then we did SEM of the filter media and looked at the fiber diameter distributions. And here for filter medium C, you see obviously it consists of 2 completely different layers, which is basically not a problem for GeoDict, but it's numerically a bit more complex because you have different size scales. So we excluded this one also from the beginning. And finally, we saw that here for this filter medium D, if you look at it, it has a very complex structure. So you have these molten spots and combined fibers. So that's also not our favorite thing we want to look at in the beginning. So we started with this filter media A and E to do our evaluation. So to model them with GeoDict, we did micro CT scans of the filter media. And from filter medium A, it looks very nice. You have a very homogeneous structure. For filter medium E, it's in principle also okay. But what you see here, obviously the thickness of the filter medium is not so well defined, and it's quite, let's say, fluffy on the top, which is sometimes a problem of finding a representative cutout of the filter medium. And you see, I don't know if you properly see it here on the screen, it's a so-called needle punch medium. So you dive with needles into the medium, and there you have these different structures, so which also needs somehow to be correctly considered in your small scale model. Okay, so we did simulations for these 2 filter media, and what you see here in the dots are the experimental values for the discharge filter medium, and the blue line is the model curve, so it fits very well for the filter medium A. So that's just the mechanical part. For the filter medium E, it fits a bit less well, and this could be caused by the effects I mentioned before, so thickness variations or these different regions from the needle punching. But in general, we are also here in the right range. When we turn on electrostatics, it also fits quite well for the larger particles. So obviously mechanics and this dielectrophoresis already works very well. We find some deviations still for the smaller particles here in the range around 100 nanometers, so in this electrophoresis dominated part. And this is something we are currently working on in the project. You have this kind of bump here, which is not yet produced in the simulations. And if you look a bit more in the contribution of these different effects, you clearly see this comes from or you would expect that it comes from dielectrophoresis. So for very small particles, they carry almost no charges, as I have shown before. So there the effect is small. For large particles, the electrical mobility is small, so they also have a small contribution, and thus dielectrophoresis works mainly here somewhere in this middle range and can give something like a bump. And we are currently looking at if this could be an effect of different charge distributions or on of the fiber charge to see where this discrepancy comes from. So in the last few minutes, I would like to give you an outlook to the implementation of these discharging effects. And just to give us an example where you see this in practice, we have, for example, have tested 8 different air cleaners and we exposed them to cigarette smoke. That's a standardized method to age them. So you burn 100 cigarettes. It's not a very nice method. And you expose the air cleaner to it and see how the so-called clean air delivery rate, you can basically for the moment see this as a filter efficiency as a function of particle size. It's just multiplied with the flow rate of the appliance. And you see there are strong differences between air cleaners. Some do not really care about these 100 cigarettes and the performance does not change at all. And other air cleaners have really strong degradation effects upon the same amount of cigarettes. And it's certainly worth to learn more about these processes and maybe also to model them. There are basically 3 ways how you can think about this degradation process. So the first is you have your charged fibers and you deposit oppositely charged particles on it, and then you get just a compensation of charge, and in the end you will end up with a neutral state. And this is, for example, if you load with salt particles, the dominant mechanism. So we have investigated this in previous projects. So if you dose salt, you end up with a completely discharged state in the end, and you can easily explain this by just this charge neutralization. But if you look here at the time scale, so the filter medium was loaded 3 days with salt, so that's a rather slow process, this decay by compensation of the charges, and that's easy to directly implement because it's just, let's say, mathematics to correctly track particle deposition and update the surface charge correspondingly. A second effect, which you often find in literature, is charge shielding. For example, if you have droplets, they form a liquid layer on your fiber, and this material has a certain dielectric constant, and this could lead to shielding of the charges. And basically, the GeoDict has ways to implement these coalescence filters, so how is the liquid distributed in the filter, and this is something we want to try if we can explain certain effects by this shielding. But unfortunately, there are more complex processes. For example, if you load with oil droplets like DHS, the decay can be very fast, and we also see this in our simulation. So that's, for example, the initial efficiency measured with salt, and if you do measurements with DHS or rather high loading of DHS, you see already during the measurement the efficiency goes down, and if you then remeasure with KCl, you end up with a state which was completely different from the initial state. So DHS has much more effect which go beyond this shielding and compensation. So it can be chemical reactions, it can be charge mobility in the polymer. But it's not realistic that we can model this in GeoDict because it's something which happens on the atomic scale. But our idea is, can we somehow have a database for different material combinations and some empirical ways, is it a linear decay and exponential decay, and to try how somehow try to implement these effects by this. So this is something we are currently working on. And as Philipp Eichhammer said, there are already some first models for this implemented in GeoDict. Okay, so to summarize, we have successfully implemented, let's say, the fundamental physics, so the deposition mechanisms, charge distribution on the fibers and on the particles. We have validated with an independent program that these are all correctly implemented. We already achieve a good agreement for the only mechanical part, and we are on the way for discharge media and currently looking where these remaining discrepancies are coming from. And we are also in the last part of the project trying to implement these discharging processes, which can be charge compensation, charge shielding, or in an empirical manner, more complex mechanisms. Okay, and with that, I would like to thank our sponsors, SIM and the BMW K, for funding this project, and you for your attention.